So, this will be our final lecture of this course on classical electromagnetism 2, and the thing that we were discussing was that if you have this if you define this H vector, you define it as B over mu naught. B is the magnetic field, net magnetic field at a point, B over mu naught minus magnetization vector, which is once again, if you have a material and it is magnetized, you have dipole moment per unit volume, that is what we call M, and this is how we define our H. And B you can write as mu naught times M plus H, the dimensions are same and the units SI unit is ampere by meter. And then with this H, if I do some algebra, we find that this part cancels out and we have this curl of H is equal to JF. This is bound current here, this is bound current here, and curl of H is JF. So, curl of H is JF, and in magnetostatics we know that curl of B is mu naught times J. So, the mathematical structure is same, and therefore, we said that we can expect that the way the total current gives me magnetic field, that is how this JF should give me H, and we found that yes, in some of the cases it works and in some of the cases it does not work. And then we went for this divergence part, and we found that okay, although the curl equation is similar, but the divergence equation is different. Curl of B is mu naught J, curl of H is JF, that is fine, but then divergence of B is 0. Here divergence of H need not be 0. It is from these equations, from the definition, it is minus of divergence of M. M is the magnetization. So, if divergence of M is 0 everywhere, then yes, this set of equation and this set of equation are identical, and the way you get B from J in the exactly similar expression, same expressions you can use for H resulting from JF. But then if that is not the case, then we are in a different situation, and for that we said okay, fine, if we compare these equations and if there is no free current, it is all because of bound currents, that means you have magnets and magnetized materials, and only because of that you are looking for the magnetic field and other things. This free current density is 0, curl of H is 0, divergence of H is this, and this looks very similar to the case of electrostatics. In place of this rho, you have here minus divergence of M. M is given to us, magnetization we know. So, we know what is this divergence of M, and you can write this divergence, negative divergence of M. Let us write this as rho H. We are writing a totally different quantity, rho H, and we will call it H charge density. H charge density. If I define this rho H by this equation, rho H is negative divergence of magnetization vector, then it is even more similar to this. This is now divergence of H is equal to rho H, and curl of H is 0. So, this equation and this equation, divergence of E is this, divergence of H is this, curl of E is 0, curl of H is 0, they are identical. So, in this situation, if you define H charge density and treat this minus divergence M as this volume charge density of this H charge, then yes, the way you do in electrostatics, you have a charge distribution, what is the electric field? Exactly the same equations, exactly the same formulas you can use here, put epsilon naught equal to 1, forget this epsilon naught, and the same expression will give you this. So, let us take some cases where we can use this, and so there are two methods. Finally, suppose our problem is that there is a magnet or a magnetized material and I want to know the magnetic field because of this, B field because of this. Now, one way is that okay, you know the magnetization and therefore, you use these equations, get the bound currents, there may be surface current densities. So, now you have currents, then use Ampere's law, Bat-Savart law, etc., to get B. And if H is needed, you can always get this H from this definition. Once B is obtained, magnetization is known, you can get this. You can reverse. If M is given, you see what is this divergence of M, so that you know what is rho H, what is this charge density. So, in the material you see what is that charge, H charge density. Once you have the H charge density, just think that you are doing an electrostatics problem. It is an electric charge and write the whatever the electric field, and that expression, accepting that epsilon 0 you have to forget or put 1 for that, is your H. And once you get H, then of course you can use this equation. Once you get H, M is known and you can get this B. So, either way you can solve this problem. So, let me show this method for some simple cases. So, first let us suppose you have a bar magnet. And the uniformly magnetized, we will take uniformly magnetized bar magnet. This magnetization is M, constant everywhere. Inside this bar magnet, outside there is no material, there is no question of dipole moment per unit volume. So, outside M is 0, M is 0, M is 0, M is 0, M is 0. Outside there is no magnetization obviously, and this is the bar magnet, right. And then we want to know the magnetic field because of this bar magnet. This is your so-called south pole and this is that so-called north pole. So, what we do? We look for the charge density, H charge density. What is divergence of M? Negative divergence of M is the charge density. Now, inside this magnet, M is uniform. So, minus divergence M is 0. So, no charge density inside, no H charge density here, because divergence of M is 0, it is uniform magnetization. Outside there is no M and therefore divergence of M is 0. So, no H charge inside, no H charge outside, then where is the charge? The charge is on the surface of this magnet. This H charge is on the surface of this magnet. You have this surface, this surface, this surface, this surface, or if it is cylinder, then this is the curved surface, and then this flat surface. Surfaces we will have to check. You can have surface charge density. The volume charge density is 0 here, volume charge density is 0 here. Now, if I look at this point here, if I look at, or let me first do this rho h d tau in a volume. Suppose I have a volume, some volume delta V, and I calculate this rho h d tau on this value, on this volume, and rho h is minus of divergence of M. This is rho h and d tau. But you also know that Gauss divergence theorem, apply that Gauss divergence theorem here, and this thing will be equal to m dot dA on the closed surface bounding this volume, right. This is pure mathematics. divergence of m d tau is same as m dot dA, and this surface on which this is to be integrated is the same surface which encloses this volume that we have taken for this integration. So, this is given by this. Now, this thing is total charge, total H charge in the volume, So, you get QH, total charge here inside this volume is equal to minus integral m dot dA on the surface, on this surface. Good. Now, let us take a volume somewhere here, let us take a volume somewhere here. So, part of it inside, part of, or you can take directly, you take a plane area here, you take a similar plane area here, and then connect the corresponding points and make a volume. What is m dot dA? What is m dot dA? What is dA vector? Here the dA vector is in this direction, here the dA vector is in this direction. M is anyway 0, so no question of m dot dA on this surface. Here m is not 0, but m is in the, let us say this is x direction. So, m is in the x direction and dA is perpendicular to that. So, m dot dA is again 0, and here also if you take, then we can take this height very small, just inside the surface and just outside the surface. In that case, the contribution from here and here will also be 0, and even in this case also, since this m is going this way and this dA will be this way, and here m will be going this way and dA will also be this way. So, this is m dot dA positive, this is m dot dA negative, will cancel out. And also I can take just inside, just outside, because I need the charge on the surface. I know that there is no charge in the interior, no charge here, charge is only on the surface. So, I can make a volume which is just outside and just inside these surfaces. So, this whole thing is 0, right. On this volume, we see that in this volume QH is 0. We know that nothing is outside, nothing is inside. So, nothing on the surface also. If the total charge is 0, then there is nothing on the surface. Now, look at this surface. Take a similar area here and an area here, very close to, you can take it very close to the surface and then join the corresponding points to make a volume, And on this volume, you calculate what is this quantity QH in this volume. So, here if you do, then this surface, look at this surface, here is dA, and magnetization is this way. So, on this surface it will be m into area with a negative sign, and this negative sign is also there. So, that makes it plus. So, on this surface m is this direction, dA vector in this direction, m dot dA will be negative capital M into this whole area. So, negative capital M into this whole area, and this negative here, that makes it plus m dA, and there is no m dA here outside. There is no magnetization. On this part, curved surface is not there, because on this part the dA will be this way, here the dA will be this way, and so on. So, this will be the total charge enclosed in this, right. So, there is a charge m times d delta A, that is the H charge contained in this, and we know that it is not inside, it is not outside, it has to be on the surface. So, that means you have a surface charge, you have a surface H charge density, And how much is that? How much is that? The charge here on this surface is this m times delta A, and divided by delta A is the density, so m. So this magnetization m itself is the surface charge density on this end, at this end. You can write that as sigma h. Sigma h, this is sigma h. Sigma is surface charge density, that is m. And similarly, if you do it here, you do a similar volume, make a similar volume, and on this volume you do this whole exercise. No m dot dA outside, no m dot dA on this part, it's only here, and here dA is and m is are in the same direction, so it will be plus. So m dot dA will be plus, and with this minus sign the charge density there will be minus m. So this is left end and this is right end. So our magnet is now, this magnet, I write this as it is having a positive surface charge density here, sigma h, which is m, and a negative surface charge density here, minus of sigma h, that is minus of m. And this whole thing is delta A, so the total charge will be this multiplied by delta H charge. This is all H charge. Now I am ready to give you H field, B field, whatever you want. So if you suppose I need H field just outside this, just outside here, what is H? What is H? Here, just outside. So we know if you have a surface charge density on a surface with this surface charge density sigma h or m, capital M, then just outside it will be sigma by 2 epsilon naught, right. Electric case, you have a charge density, surface charge density is sigma on a surface, and then you go just outside, sigma by 2 epsilon naught. So this h will be, this h, because of this h will be m divided by sigma by 2 epsilon naught, and epsilon naught we have to forget. Okay. So sigma by 2 epsilon naught. In the electrostatic case, epsilon naught we have to forget or put 1. So it will be sigma by 2. So m by 2, that is because of this. And how much is the H field because of this? If this length is L and this is the area, on this area this H charge is distributed with a negative sign. So if this capital L is large as compared to this this width here, at least we can write a simple expression, and this is H1 and H2 because of this H1, this is because of this H2. If this L is reasonably large as compared to this, then you can say that okay, total charge I can take like a point charge, and that total charge will be now this m times delta A, negative, remember negative, and divided by 4 pi epsilon naught. I do not have to write epsilon naught, remember, L square, and therefore this H will be m by 2 here, and then minus m delta L delta A and 4 pi L square. I know H here, anywhere here, anywhere you want H in between here, what is H? So if this L is large, we will say that okay, because of this it is this way, because of this also it is this way, and then this H will be double of what? Double of total charge m delta A, this is the total charge, divided by 4 pi epsilon, so 4 pi, and L by 2 square, L by 2 square. So you can just use your electrostatics to write this H, and once H is known, B is anyway known. B is mu naught times H plus M. So, you can do it this way. Another example I can take, one more example which is interesting, is uniformly magnetized sphere. Suppose you have a uniformly magnetized sphere. This is M everywhere, M uniformly magnetized. If I go through this route, we can do that. We can go through this route. Once again, divergence of M is 0 inside. Once again, divergence of M is 0 outside. So, it will be this H charge density can only be on the surface. It can be a surface charge density. We can use the same technique. Let us say this is Z axis. Here is the origin, and you take angle theta. You take a small area here, think of this a small area here, and then parallel to this you construct one area here, and then you join them and make the volume. And in this volume you calculate, or surface of this volume, what is this m dot dA? What is this m dot dA? So, m is now in vertical direction. Look at this surface. M dot dA will only come from this surface. This surface there is no magnetization, and other places you can take very small thickness of this volume, and therefore that part will be 0. So, it is only on this surface, and here the magnetization is this way, and the dA vector is this way, radial. That is the dA vector. So, this will be m into area, this area, small area. So, I can do this integration this way, and then cos of theta. So, this is cos of this angle, which will be negative of cos of this angle, and this angle is same as this angle, and this is our theta, the spherical polar coordinate theta. So, cos of this. The negative will cancel with this h. Here it is a negative, but the charge, when you write, what is the charge? Is negative of that. So, m delta A cos theta is the charge, and what is the charge density? It is m cos theta. H charge density is m cos theta everywhere. Now, remember, in electrostatics we have this problem that if sigma is sigma naught cos theta, find electric field. Find electric field. And in this course also I have used it. In the chapter of vector potential I have used this result, and the result is very nice, that if you have this kind of surface charge distribution, positive charge this side theta equal to 0, pi will be minus 1, so it will be this. So, everywhere it is there, the charge is everywhere there, but then the density is different. For this kind of charge distribution on the surface, remember it is on the surface, the electric field turns out to be opposite direction, this direction, and uniform. E is minus sigma naught, this one, and divided by 3 epsilon naught. We know this from electrostatics, we know this, and our situation is exactly the same. The H charge density is on the surface of a sphere, and it is m cos theta, m is constant, sigma naught cos theta, sigma naught is constant, and therefore we can directly write from this H inside. I am only writing inside, outside also you have H, here also outside also you have your electric field like dipole. So, those things will be there, will come like this. So, all right, it's like dipole field. So, it will be there, but inside, let us write inside, H inside will be minus m over 3, no epsilon naught. This will be H inside. Okay. So, if this is a sphere and I ask what is H, the H is like this. How much is the magnitude of H? The magnitude is this minus m by 3, and here is the direction. Magnetization is this way, H is this way. Natural, because you have positive H charges here, negative H charges here, therefore the H field has to be downward. So it is this. And what is B? What is B? B is mu naught H plus M, and this is mu naught, what is H is minus M by 3 and plus M. So it is 2 by 3 mu naught M in positive direction, M direction. So that is, if you ask for the B vector, the B vector is this way, this B vector is this way. This is our H vector, H lines, these are H lines and these are B lines. So B lines are this way, and the magnitude here is B is equal to 2 over 3M. So this is a way to calculate magnetic field with magnetized material. The two remarks, one is now it looks justified to say that a bar magnet at the ends, they are different, one side is positive H charge and other side is negative H charge, and that north pole, the pole that we say, we can give this name pole to this charge. So you have negative and positive poles, or north or south poles, right, and then the similar charges will repel and the opposite charges will attract. All those electrostatics thing qualitatively and quantitatively you can use with this magnet. So that is one justification of saying that there are two different kinds of poles and similar poles and dissimilar poles and all those things, and then making calculations can be justified if we do this analysis this way and write our correct H charge there, which you can pole, and that charge density you can say pole strength. So all those things can be done, but the second comment, this H charge is not there, it is our mathematical construction. The B field is there, the B field is real, the B field is real, the magnetic field is real, magnetization is real, but then we are constructing a quantity, mathematical quantity H, which is B by mu naught minus capital M, calling it H, and then we find that okay, this H has very good properties. Divergence of H is something, curl of H is 0 if there are no free charges, and therefore we can use this electrostatic analogy. So we do not have real H charges, we do not have H surface charge density at the end of the magnet, we do not have, but then this model is very good. This model is very good. If we replace the magnet by this positive and negative H charge densities, it will give me the H vector and B vector in some cases much quickly than going through that equivalent current and other things. Alright, so with this remarks I end this lecture. It was a very nice experience for me to prepare all these lectures for this course, and many of the things which were not current in my mind, I revised everything and learned many things here, and very nice things. So thank you all, thank you the team, Shiksha Supan team for recording, Mookit team for managing and all. So thank you very much, have a nice time and enjoy physics.